Welcome back, everyone. Today, I'm going to be doing something that might seem a little off topic, but I assure you in the next video, it's going to come back around to more derivative rules and proofs. But I want to talk about Euler's identity. It's a very famous equation. Technically, the original is e to the I pi plus 1 equals 0, but this is equivalent. E to the I pi equals negative 1. It's a very beautiful equation using some of the craziest mathematical constants all in one. But why the heck does it work? And so to talk about this, we'll have to discuss e to the x versus e to the ix. Now, for the uninitiated, I denotes the imaginary number, or by definition, the square root of negative 1. Now, if you try to find the square root of negative 1, you'll find that no real number satisfies the equation, and thus we denote it using I. Now, the real number line exists here, while the complex or imaginary number line exists perpendicular to it to form the complex plane. And you can have numbers like right here, which can be described as 2 plus 2i. Now, you've probably seen this even before you take calculus, but what bearing could this possibly have on the actual real world? Well, that'll come in the next video, but today I want to discuss what it means to raise something to an I exponent. First, we must discuss how multiplying by I works. Say you have a number, 1. If you multiply by I, it of course goes to I. If you multiply I by I, then you get I squared, and since I equals the square root of negative 1, I squared must by definition be negative 1. And so we go from 1 to I to negative 1, and of course, you multiply negative 1 by I, you're going to get negative I. So you're going to come down here. Negative I times I. Well, if I times I is negative 1, there's another negative there. So it loops all the way back to 1. What does this mean? It means that when you multiply a number by I in the complex plane, it will rotate it by 90 degrees in the complex plane. Now think about this. If we put I in the exponent, what could that possibly mean? Well, it can't exactly exist on just the real number line if x is anything other than 0. Of course, if x is 0, then the whole thing is 0, and it's just e to the 0, which is 1, of course. But it seems like no matter what we put into x, as long as it isn't 0, we must have some imaginary solution, right? Not quite. Let's consider the starting vector. If e to the 0, right, x is 0, we'll have e to the 0, which is, of course, 1 right here. The distance from 0 to 1 is going to be considered as the position vector, right? If it were e to the x, when x is 2, then it'd be e squared. If x is 3, it'd be all the way out here. And you get the idea. As x increases, that vector, that position vector, will increase. Of course, on just the real number line, every vector is just a line. But on the complex plane, it actually does have a proper direction. Which means that for e to the ix, we need to consider what happens when x increases. And to do this, we need to consider the rate of change of the function. Wait a minute, what's the rate of change of a function? Its derivative. Since I is still just a constant, we see by the chain rule that the derivative of e to the ix is equal to I times e to the ix, meaning that the velocity of the function, right, the rate of change, the speed, the velocity, is always going to be I times whatever it is in terms of position, since e to the ix is the original position function. What this means is that given any position vector, we're multiplying by I to get our velocity vector, and the magnitude is the same. Which means, like we discussed earlier, when you multiply by I, you have to rotate 90 degrees. So if this is the position vector, this must be the velocity vector, which means that as x increases, our initial velocity vector is straight up. But once it goes straight up, our position vector is going to look like this, right? It's slightly different, which means our velocity vector is going to look slightly different. And this should make sense. The derivative looks slightly different at every value of x. But what you'll see is that as this keeps changing, say we have here, and then here, and then here, we see that it creates a perfect circle. We can actually see this concept in real life if you take two things, any two things really, tied together. Now, if we write with this one, and we keep this as a center, and we pull the string taut, then as I tug perpendicular to the string, and I keep this centered, what we get is a perfectly circular arc. Now, as we see, tugging perpendicularly to whatever the position vector is, that string, creates a circle. And the exact same thing is happening with e to the ix. So with that in mind, we look back at this unit circle in the complex plane that is created by e to the ix. Now here's the thing. Because the distance traveled is proportionate exactly 1-to-1 to the actual amount of time passed, that means that for any angle that we have here, call it theta, it will take x amount of time to travel x amount of distance. What does this mean? It means that whatever our input x will travel that far around the unit circle, and thus that angle theta will be exactly x radians. Now, I'm assuming since you're taking calculus, I'm assuming you're taking calculus if you're watching this, that you already know what radians are since you've probably already taken trig. But this means that e to the ix, for any x, you will get whatever the vector is of magnitude 1 of angle x on the complex plane. Now what's a half circle? A full circle is 2 pi radians, so a half circle, to get from here to here, would be pi radians, which means you need to plug in pi into the exponent here. You'd get e to the I pi. And what does this equal? Well, we see magnitude 1, so it has to trace this circle, and 180-degree rotation, we get -1. Isn't that just beautiful? Now, I know this topic is very difficult. If you want another video going more in depth on this, please let me know in the comments, but hopefully it wasn't too crazy, and thank you so much for watching.